All right, good morning, everybody. We're going to talk about inductors today. And I am recording this in the morning that you're going to see it. So I want to say something else to you. If you're watching this, today is the first day that they're going to be offering the live web session for AP Central. I think that if you want to watch that, I want to see what it is, but it's not on material that we're going to be having on the exam, but it'll give us an idea of what the quality is going to be. Please check your email for the times. All right, talking about inductors today, and to understand what inductors are, it helps to have a little bit of a quick history about capacitors. And a brief reminder of what a capacitor is a device that we found was really attempting to ramp up this idea that you could enhance and kind of harness the electric field that was between two parallel plates. That this device would allow you to store charge, that for whatever reason, because of the strength of the electric field or the nature of the metal that was there, we could grab charges from one plate and add them to the other plate, and we can get a buildup of charge. We can't get a buildup of charge anywhere along the wires. So we know that the electrons space themselves out in the conductor, but we could add more charges to one conductor and take them from the other conductor. And by doing so, we were creating an area where energy was being saved. In fact, we know that in the end, the amount of energy being saved is 1/2 CV squared. And we know that the actual size of the capacitance is related to how much charge it stores. And remember, it's a ratio here. The top part is the charge part, clearly, but the bottom part is what drives those charges, or is the pressure on those charges, which we call the voltage. We know that there's also another side to this, which is how you construct a capacitor. And the construction of the capacitor, although it involves epsilon naught, we know it really involves the shape of the capacitor, the surface area of the plates, and how far apart the plates are from each other. These are the real things that dictate the size of our capacitor. So there's the how a capacitor is used definition, and then there is how you construct a capacitor. And if you think back to when we were looking at capacitors initially, the way we came up with this relationship was by starting with a particular shape we thought could work, a parallel plate, and we used this function to kind of decide how much charge would fit for a given voltage. We use Gauss's law, ultimately, to find out what the electric field was between the plates. We then calculated the work done in moving a charge from one side of the plates to the other. And from that, divided by the charge, to determine what the electric potential would be between the plates. So it wasn't an applied electric potential, it was an electric potential that we calculated based on the electric field you'd get from a certain charge. And when we substituted in the solutions here, we received an equation that told us the geometry of our situation and what it would contribute to the capacitance of our device. So, inductors are similar in that we know that inductors can store energy. We knew capacitors could store energy, but inductors store energy in a magnetic field. So, just a couple of station keeping kinds of things. The symbol we're going to use for inductors is a coil Mostly because we know that a solenoid is one of the best ways for us to store a magnetic field, and we know that in a solenoid the calculation of a magnetic field is relatively straightforward, and we know that inside a solenoid the magnetic field is uniform. So there's a lot of good reasons to use a solenoid as our basis for an inductor. We are going to define inductance as the flux, the magnetic flux inside our device per unit current. Now again, there are significant comparisons here to capacitance. I mean, capacitance is charge per unit voltage. Inductance is flux per unit current. So clearly, inductors are current devices, meaning that they are driven by current, while capacitors are voltage devices. So I don't think that's a surprise. We know that the magnetic field is created by the movement of charged particles, so it's not too crazy that there would be energy associated with that movement of charged particles. The top part, of course, of the capacitance equation is all about charge. It shouldn't be too big a surprise that we're not looking at charge here when it comes to the inductor. So what's the real place where our magnetic field energy is stored? Flux being such a huge part of Faraday's law, it really shouldn't surprise you that it is the flux that contributes to our calculation of inductance. Now, I had you guys for homework yesterday take a look at the Henry, which is the unit of inductors, and I hope that you took a moment and did that, because it'll give you an idea of it's a little about how complicated that is. And we're going to use the Henry clearly, but most inductors have millihenry or microhenry measurements in the same way that most capacitors were millifarads or microfarads. I do have a couple of big inductors at the classroom. If we get back, we'll take a look at them. What I found, and this is a problem with inductors, and we'll talk a little bit about it as we go on. Inductors are a coil of wire. So you can do things to enhance the inductance the same way you can do things to enhance the capacitance. But an inductor stores its energy when the charge is flowing. Now, that might not seem like a big deal right now, like what's the difference? Well, capacitors store their energy when the charges are stopped. But because an inductor stores its energy when the charges are flowing, the first thing you have to understand is that you have to find a way to construct your circuit in such a way that the charges continue to flow. The capacitor, we could open the switch after it was charged, and that charge would stay with the capacitor. We could use it at any time. But in an inductor circuit, I mean, let's just think of a simple LRC. I'm sorry, just not LRC, a simple LR circuit. I'm going to try and grab just the inductor here. We're going to have our battery, our resistor, and of course we probably should put a switch in here. So if I want to show that the energy is actually available in the inductor, I'd close the switch to charge to get the currents flowing so I can get some energy into that inductor, but I can't open that switch and take that energy somewhere else. If we look at just the equation for inductor, I haven't looked at the energy yet, but an inductor's inductance is based on the flow of charges. That magnetic field is only going to be there when the charges are flowing through the inductor, which means the only way I can use the energy in that inductor is if I use it while the electrons are still flowing through it. So inductors have to be kind of used a little bit differently because their energy has to be maintained while the flow of charge is maintained in the inductor. So without too much craziness, let's take a look at the building of an inductor. We'll do that first, and then in class today we're going to talk a little bit about the use of an inductor. So how do you build an inductor? You start with a coil of wire, and it's a solenoid clearly. And we've used Ampere's law to figure out what the magnetic field inside a solenoid is. But let's take it a little bit further and talk a little bit about the construction of a solenoid. If we use Ampere's law, we know that from Ampere's law we would have to use a loop like so. To calculate the magnetic field inside an inductor. But we already know that the magnetic field is mu naught lowercase n times I. It's the magnetic field that flows inside an inductor. Now we could also write this as mu naught n over, in this case it would be the length, times I. So right there, that is the magnetic field that is inside an inductor. Now we get that from Ampere's law, and I don't really think we need to go back through that. I used to say it would be worth memorizing, but it's not going to be on the exam, so it's worth knowing, I guess. There's really only the one thing that's important there, that it's the raps per unit length. That's really what ramps up the size of that magnetic field. But remember, our inductance is based not on the magnetic field, but the magnetic flux, which means we need something to describe this area. And we could just say area, but that would mean that the flux would be, here's where it's going to be a little more tricky, NBA. And I don't mean the basketball association. B is the size of the magnetic field we just talked about. A has to be the area, and N would be the number of turns. Now I could have gone the longer route here, and I hope that many of you who are watching know why I didn't. We could have done this as N times the integral of B dot dA. But the reason we choose a solenoid is because a solenoid has consistent magnetic field across its whole area. So we don't really need to do the integral. The magnetic field is uniform inside the loops of a inductor, or inside the loops of a solenoid. So we know that all we really have to worry about is whatever the cross-sectional area of our inductor is. So that's why I didn't go through the whole calculation there. Now, quick substitution gives us part of this. And I want to be a little careful here. I'm going to choose this one. And that's because n is the number of loops. The capital N is the number of loops, and that way I have a consistent variable between the two. So number of loops times mu naught n over L times I, all times the area, which gives me, for the flux, this number of loops squared. I didn't plan that out real well. Let's do it this way. Number of loops squared over the length times the area times mu naught times I. Now, that's the flux based on a standard solenoid. And there's some obvious things I think that are apparent here, and I kind of put them towards the front, that we have this geometric kind of piece, something that we saw before in capacitors, a geometric piece. We have something about the space inside the inductor, just like we had something inside the space of a capacitor. And of course, we wouldn't be doing this without the current. The current flow determines the magnetic field. But remember, inductance isn't about how the object is necessarily being used at that moment. It's a general relationship about the ability of the device to store energy. So when I look to calculate what the inductance would be of a standard solenoid, I take the flux, put it in the top of that fraction, and divide by the current that I would use in my circuit. This gives me an expression that is all about the shape and size of my device. And I'm going to change the order of things here a little bit, because I think it makes perfect sense to consider this when compared to a capacitor. First, I have something about the space inside the inductor, the permeability constant here. which is why we probably wouldn't have empty space inside our inductor. We'd probably fill it with something that would enhance the magnetic field, like iron or something. Number of loops, so if I have lots more wraps of wire, and this is the physical number of loops, 100 loops, 1,000 loops, whatever. And then a geometric portion, cross-sectional area versus length. Now, it shouldn't be a surprise. I want my inductor to not be very long, but to have a large cross-sectional area that ramps up the inductance. On the other hand, we don't know how the inductor is going to be used. So whether we want a small inductance or a large inductance really remains to be seen. We saw in our capacitor circuits that the rise time was clearly dependent on the capacitance. If I wanted to take longer to charge, I needed a bigger capacitor. If I wanted to take less time to charge, I needed a smaller capacitor. So I think we might end up waiting to decide what makes for a good inductor. Do I want a large value for inductance or a small value for inductance? We'll need to look at the energy and such for that. And I'm going to save that for our class discussion. So there you have it. That's how you create an inductor.